Welcome to today's class. In this tutorial, I'm going to teach about momentum and Newton's second law of motion. Starting with momentum, I will definitely define the term momentum right away by simply saying that momentum is always the product of mass of a given body and the velocity at which that body is moving at. So momentum is equal to the product of mass of a body and the velocity of that given body. The velocity of a given body and the mass. The product of the mass and velocity is equivalent to the momentum of that given body. Now, for example, initially, the initial velocity of a body is usually denoted by u. So when you have the initial velocity of a body, initial velocity of a given body is always denoted by a letter small u, and the final velocity of any given body, because when a body moves, there's that velocity at which it starts to move with, and the velocity which it stops with. So that initial velocity is denoted by u, and the final velocity of that given body is denoted by v. Now, momentum is the product of the mass. So we can find now the momentum, which is denoted by capital P, is equal to the product of mass of that given body. So the mass times the velocity. So you take mass and you multiply by the initial velocity, that is u. This one gives you mu. So mu is the mass and the product of mass and the initial velocity of this body. So such kind of momentum, because this one is initial velocity, so this one is known as the initial momentum of a body, initial momentum of any given body. Then when you find momentum P, when you take the momentum P, which is the product of mass, the momentum when you take momentum mass times the final velocity of the body, mass m multiplied by v final velocity, this gets you mv. So this is now referred to as the final momentum of a body. The final momentum of a body. The difference between the final momentum and the initial momentum is known as the change in momentum. So when you have something known as change in momentum, this one is the same as change in momentum is the same as the final momentum of a body. The final momentum minus, you subtract 2, the initial momentum. So the final momentum, the change in momentum is, we can notice as change in P is equal to the final momentum, that is the same as mv minus the initial momentum of this given body is known as mu. So you take mv minus mu, that gives you the change in momentum. Now, without wasting time, let me talk about the Newton's second law of motion. This guy, Newton, came up with a law, 3 laws of motion: the first law, the second law, and the third law of motion. So today I want to talk about the Newton's second law of motion. The second law states that the rate of change in linear momentum, the rate of change in linear momentum is directly proportional to the resultant external force and takes place in the same direction. Is directly proportional to the resultant external force, and takes place. So it should be the rate of change direct proportional to the resultant external force and this force should take place in the same direction, resultant external force, and takes place in the same direction as the momentum, and takes place in the same direction. In the same direction. Now, during the derivation of the change in momentum, from the second law of motion, Newton's second law of motion, which said that the rate of change in linear momentum is directly proportional to the resultant external force and takes place in the same direction. Now, the change in momentum of a body, the change in linear momentum. Change in linear momentum, we say that when you have the change in P, the change in P is the same as mv. That is the final momentum minus the initial momentum. But now when it goes with the rate of change, the rate of change simply means the change in momentum with respect to time. So the rate of change is the change in momentum with respect to time. So this is the same as the change in momentum mv minus mu over t. But now when you substitute m outside on the right hand side of the question, taking m outside into bracket, substituting m, because it is a common factor in mv and mu. So that gives us m into bracket v minus u over t. This one is the same as the rate of change in linear momentum. And this rate of change in linear momentum, from the second law, it is directly proportional to the resultant external force. Directly proportional to the resultant external force. So that we have mv minus u over t. V minus u over t, this is the same as the acceleration of the body multiplied by ma is directly proportional to the force. That is the resultant external force of that given body. So, if F is equal to, removing the proportionality sign, we introduce a constant K, ma. But if K is equal to 1, given that K is equal to 1, so the force is equal to the product of mass of that given body times and the acceleration. The mass and the acceleration. The product of mass and acceleration is equal to the force of the resultant external force which takes place in the same direction. Now, from the definition of the Newton's second law of motion, we have derived up to a point whereby the equation connecting force, mass, and acceleration is the same as force is equal to mass times acceleration F. This one implies that F is equal to ma. F is equal to ma. Now, let me answer the questions I've written on the board for today. Question number 1. Question number 1 reads, a bus of mass. So the mass of the bus is equal to 2,500 kilograms. 2,500 kilograms. Initially moving at 20 meters per second. So the initial velocity of this bus, that is u, is equal to 20 meters per second. Calculate the force needed. So the force needed is what we want to calculate. F is equal to what? Calculate the force needed to bring the bus to rest. So when a bus is moving, when a body is moving and that body is brought to rest, this implies that the final velocity of this body is reducing to 0. So the value of v is equal to 0 meters per second. So that is the value of v to rest over a distance of 20 meters. So the displacement there is equal to 20 meters. Calculate the force. Now, the force from the Newton's second law of motion, the force is equivalent to the product of mass and the acceleration. That is from the Newton's second law of motion. So this force is equal to mass, acceleration is equal to the change in velocity v minus u over t, where v, This V stands for the final velocity, U stands for the initial velocity, T stands for time, M stands for mass, and F is the force. So, from the constants given, we have been given the mass, we have the mass, we have the final velocity, we have the initial velocity, we don't have time. But at the same time, we need to find the acceleration of the body. We can find the acceleration of the body. Now, the question comes, how are we going to find the acceleration of this body? Now, we go back to the equations of linear motion. The first equation, which is V is equal to U plus AT. Second equation, S is equal to UT plus a half AT squared. And the third equation, number 3, V squared is equal to U squared plus 2AS. V stands for the final velocity, U stands for the initial velocity, A stands for acceleration, T stands for time, S stands for displacement. Now, we don't have the acceleration. We can get the acceleration or we can get the time. So F is equal to ma. So I can use the first equation to get the acceleration. But now we don't have time from the constant given. So the first equation is not going to help us because we don't have time. We have the final velocity is there. The initial velocity is there. We don't have acceleration. We don't have time. Equation 2. The displacement is there. We have displacement. We have the initial velocity. We have time. And we are looking for the acceleration. So it means that we can use the second equation. So using the second equation, S is equal to UT. S is equal to UT plus a half AT squared. But the displacement of this body is 20 meters. So 20 meters is equal to UT. We have time, we don't have time. Let me go back to the third equation because we don't have time, we don't have the acceleration. So let me just write the three equations. V is equal to U plus AT. I just said that we don't have time in the equation. S is equal to UT plus a half AT squared. And the third equation is V squared is equal to U squared plus 2AS. And I told you that V means the final velocity stands for the final velocity, U stands for the initial velocity, and A stands for acceleration of the body, and S displacement. Now, the initials given from the equation, we don't have the acceleration, we don't have time. So I really feel that the equation 2 is not going to help us at equation 1 because equation 2 has time and acceleration. So you cannot get the two unknown because it is only one equation. So simply I can use equation 3. So we have V squared. V is there, U is there. Acceleration is not there, but displacement is there. So this equation is going to help us, equation 3. Now, from the formula, V squared is equal to U squared plus 2AS. So V squared, we just do substitution, that is 0, is equal to U squared, that is 20 squared plus, into brackets, 2 multiplied by the acceleration A times the displacement, which is 20. So in this case, when you find the value of A is equal to negative 10 meters per squared second. So that is the value of acceleration. When you get negative, it means that the body is decelerating uniformly with the time. Now the value of A is equal to negative 10 meters per squared second. Going back to the question, calculate the force. So applying this formula, force is equivalent to the product of mass of a body and acceleration of that body. So force is equal to mass times acceleration. So the mass of the body is 2,500. Then we multiply by the acceleration of this body. which we have obtained -10 meters per square second. So the answer is 25,000, -25,000 newtons. Negative means that the force is applied in the opposite direction to that of the motion of the body. Now, question 2. We have two questions. A body of mass m, initially at rest. That is question 1 we are done with. So the mass of the body, mass, is equivalent to m. Initially at rest. So when a body is at rest, it means that the initial velocity, the value of u is equal to 0 meters per second. That is the value of u. The mass of the body is m kilograms. Let me just assume it is given in kilograms. Is acted on by a force. So the force is equal to F. Force is equal to F. For a time, t seconds, for the time is equal to t. As a result, its velocity changes from to final value. So the final velocity, v, is equal to v meters per second. Show that the gain in kinetic energy is equal to a half mv squared. So the kinetic energy of a body is the energy possessed by that body while that body is in motion. So the kinetic energy, this one is equal to the energy of a body in motion. Energy of a body in motion. Now, to derive that E is equal to a half mv squared, so the energy of any given body, energy is equal to the force times the displacement of the body. The product of force and displacement of the body is like a torque energy. It's just like a torque, like the moment of a force. The only difference between the energy and the moment is that the moment of a force, the displacement of the body is perpendicular to the force. Now, the force of a body is equal to the mass of the body multiplied by the acceleration. So this is the same as mass times into brackets. Acceleration of a body is the change in velocity v minus u over t. So that is the force from the Newton's second law of motion. But now the displacement, this d stands for the displacement of a body, is usually denoted by s. This is the same as force multiplied by the displacement. Let me put the arrow because these are vector quantities. So the force is equal to m into bracket v minus u over t. But from the three equations of linear motion, the second equation states that displacement s is equal to ut plus a half at squared. Since the body is starting at rest, the displacement s is equal to u, but the u is 0 multiplied by t plus a half at squared. So displacement is equal to a half at squared. So this is the equation for displacement of that given body. The same thing applies to force. The body is starting initially at rest. So this force is equal to m into bracket v over t, because it is starting initially at rest. Now, from this equation of energy is equal to force of the body and the displacement, the product of force and the displacement of the body. So the force of this given body is mv over t, because the body is starting at rest. So the value of u here is 0 multiplied by the displacement of the body, a half times acceleration times t squared. So t by t1 by t times. So the energy is equal to mv times a half at. But the value of a, this value of a, acceleration, energy E is equal to mv times a half times a. Acceleration is v minus u over t. This acceleration, v minus u over t, then you multiply by t, because acceleration is times t. But this guy u, remember that the value of u is 0. You don't need to give up on the way. So E is equal to mv times a half. The value of u is 0, so it is a half times v over t. This one reduces to v over t, then multiply by t. So by t, so the equation becomes a half mass, that is m, v squared. So the energy, the gain in kinetic energy is given by E is equal to a half mv squared. So that is the proof that the gain in kinetic energy of a body initially at rest is given by the equation a half mv squared. Thank you for your time and have a nice day.